Welcome to English Learning Podcast, Throw Science.
Today, we're plunging into, well, one of the universe's most mind-boggling phenomena, black holes.
Definitely mind-boggling.
Our mission for this deep dive is really to extract the most important nuggets of knowledge from the sources you've shared. We want to give you a real shortcut, a shortcut to being well-informed about these incredible cosmic entities.
Yeah, absolutely.
So get ready, because we're about to explore concepts that are just so extreme, like gravity so strong that nothing, not even light, can escape.
And that's exactly what we're going to try and illuminate today. We'll clarify the core concepts, what a black hole truly is, the different types that exist out there in the cosmos,
Right.
and some truly astonishing facts, things that might fundamentally reshape how you think about space and, well, time itself.
Reshape reality, almost.
Kind of, yeah.
Ah.
Our goal is to connect these ideas to, the broader understanding of our universe. Why does this stuff matter?
Okay, perfect. So let's start with the absolute basics then. When we talk about a black hole, what are we actually describing?
Okay, so at its core, a black hole is a region in space-time, a place where gravity is so incredibly powerful.
Unimaginably strong.
Exactly. So strong that nothing, not even light, and light's the fastest thing in the universe, right?
Right.
Even that can't escape its pull.
And why is the gravity that powerful?
Well, it comes from an enormous amount of matter being squeezed, like compressed into an unbelievably tiny space.
Squeezed down.
Yeah, think of it as a cosmic compression event. This typically happens when a very massive star reaches the end of its life. It's quite a dramatic finale.
That concept of gravity being so overwhelming is just incredible. But, okay, if not even light can escape, that means they're invisible, right?
Right, black.
So how on earth do we even know they're there? I mean, how do scientists study something they can't actually see?
That's a really crucial question. And you're right, we can't see a black hole directly, but what we can do is detect its presence by observing its profound influence on its surroundings.
Okay. Like it's effects.
Precisely.
Yeah.
Imagine seeing a star, maybe, orbiting what looks like empty space.
Weird.
Or gas spiraling inwards at incredible speeds, heating up like crazy, and emitting X-rays just before it vanishes over the edge.
So you see the stuff around it acting strangely.
Exactly. Those are the telltale signs. It's a bit like feeling the pull of an unseen magnet. You don't see the magnet itself, but you definitely see its effect on, say, nearby metal filings.
That makes sense. Okay, so we're talking about these regions of extreme gravity, but what I find really fascinating is that not all black holes are the same size, right? They're not all created equal.
No, absolutely not. There are distinct types out there.
Can you walk us through them?
Sure. We mainly categorize them by their mass. So first we have stellar black holes.
Stellar. From stars.
Exactly. These are the most common type, formed from the collapse of those massive stars we just talked about. They're typically, say, a few times to maybe dozens of times the mass of our own sun.
Okay, so star-sized, relatively speaking.
Relatively, yes. Then at the completely opposite end of the spectrum, you have supermassive black holes.
Right, the giants.
Oh, absolutely colossal. Millions, or sometimes even billions, with a B, times more massive than our sun.
Billions, wow.
Yeah. And what's really remarkable is where we usually find them. They're typically right at the very center of almost every large galaxy.
Including ours.
The Milky Way.
Including our own Milky Way. We have one called Sagittarius A right at the heart of our galaxy.
Okay, so stellar, supermassive.
Yeah.
And I've heard about a third type, something sort of in between.
That's right. There's the intermediate black holes. They're a bit of a bridge category.
A middle child.
Sort of. Larger than the stellar ones, but significantly smaller than the supermassive giants. Their existence was theorized for quite a while, and finding concrete evidence for them has been trickier. But we are starting to gather more proof.
That's exciting.
It really is. And if you think about the bigger picture, the existence of these different types, especially those supermassive ones sitting right in the galactic cores,
Right.
it strongly suggests they play a fundamental role.
In how galaxies form. Exactly. In galaxy formation and evolution, there's even research suggesting they might act like cosmic thermostats.
Thermostats? How?
Well, the intense radiation blasting out from near the black hole as material falls in could heat up the surrounding gas and actually prevent too many stars from forming too quickly. So they sort of regulate things.
Keeping a balance. That's fascinating.
It strikes a really delicate balance in their host galaxies.
Okay, so we understand how these incredible things form, their different scales. But what happens if something actually gets too close? That brings us to the event horizon,
Yeah.
right?
Yes, the event horizon. That is indeed the ultimate edge. You can think of it as the point of no return in space.
The boundary line.
Absolutely. Once something crosses this boundary matter, light, anything, it can never escape, ever.
Never, ever. Why not?
Because at this point, the escape velocity,
Yeah.
the speed you'd need to travel to break free from the black hole's gravity,
Yeah.
it actually becomes greater than the speed of light itself.
Whoa. Faster than light speed needed.
Exactly. And since Einstein tells us nothing can travel faster than light,
Nothing gets out.
literally nothing, not even light itself has enough speed once it's crossed that line.
Yeah.
It's a concept that really challenges our everyday understanding of movement and escape. It's not just theoretical, it's a physical boundary.
The event horizon already kind of twists your brain. But what happens when we push these concepts even further? Let's talk about some of those really mind-bending implications. Like, I've heard time actually moves slower near a black hole. How is that even possible?
Yeah, that's one of the most profound consequences of Einstein's theory of general relativity. And black holes are nature's ultimate laboratory for testing it.
So it's real. Time slows down.
It absolutely does. Time truly moves slower for an observer near a black hole compared to someone far away from it. It's called gravitational time dilation.
Gravitational time dilation.
I mean, this isn't just some quirky side effect. It fundamentally shows us that time isn't universal. It's not ticking at the same rate everywhere.
It's relative.
Exactly. It's relative to your position and how strong the gravitational field is where you are.
Yeah.
Gravity doesn't just pull on things. It actually warps the fabric of space-time itself.
Space-time warping.
Yep. So, if you were watching someone fall towards a black hole from a safe distance, they would appear to slow down as they got closer to the event horizon. Slow down, almost freezing at the very edge from your perspective.
Deeply weird. Wow. Okay, and then there's that other astonishing fact about density. If Earth, our planet, somehow became a black hole, it would shrink down to the size of a peanut.
Yeah. Isn't that incredible?
A peanut. It sounds almost comical, but also kind of terrifying. So if Earth were a peanut-sized black hole, could I, like, flick it across the galaxy, assuming I had, really strong hands?
Well, it's hard to even wrap your head around that level of density, isn't it?
For sure.
But no, you definitely couldn't just flick it. Because even though it's tiny, it still has the entire mass of the Earth packed inside.
Ah, right. Same mass, same gravity.
Exactly. That peanut-sized object would still exert the same gravitational pull as Earth does now. So while it's visually minuscule, its immense mass would keep it gravitationally bound right where it was. It would still orbit the sun, just like Earth does now.
Okay, so no flicking.
No flicking, though our sun might have some thoughts about its new super dense neighbor. But yeah, it really just emphasizes the extreme compression of matter that's involved in making a black hole.
Absolutely extreme. Okay, and one last practical question maybe. For those of us listening who might be wondering if we need to start packing our bags, how close is the nearest known black hole to us? Are we in any danger?
Thankfully, no. We're quite safe. The nearest known black hole to Earth is called Gaia BH1. It's about 1,600 light years away.
1,600 light years. Okay, that sounds pretty far.
It's a very safe distance. Far enough for us to observe and study these things without any risk of direct interaction. Plenty of breathing room.
Good to know. Phew. Okay, so wrapping this up. What does this all mean for you, for someone listening who's curious about the cosmos? Today, we've really taken a deep dive into black holes.
We certainly have.
We've uncovered their immense gravitational power. We've understood the different scales they come in, from stellar right up to those supermassive giants. And we've grappled with that chilling, absolute concept of the event horizon, that point of no return where even light gets trapped. It's been an incredible journey through some seriously complex ideas.
Indeed it has. And I think it's important to remember that black holes still represent some of the most profound ongoing mysteries in astrophysics. We've really only scratched the surface today.
How much more to learn?
Oh, absolutely. For instance, scientists are still intensely debating the exact ways supermassive black holes form and grow so huge. How did they get there so early in the universe?
Right.
And there's active research into whether tiny primordial black holes might exist. Leftovers from the very early universe, could they still be around?
Primordial ones. Wow.
Yeah, maybe even making up some of the universe's elusive dark matter. It's an open question. Black holes truly push the limits of our understanding of reality, of gravity, of the very evolution of the universe itself.
As the exploration continues.
Always more to explore. They pose these profound questions.
Absolutely. Which leaves us and you with a thought. What other extreme phenomena are out there in the universe just waiting to challenge our perceptions of what's possible. What other deep dives are waiting for you?
Keep looking up.
Definitely. Keep exploring, keep learning, and keep wondering about the incredible universe we live in.